Good morning, everyone. My name is Zhe, and today I will present a talk handling noisy data in machine learning modeling and predictive control of nonlinear processes. And this work is done with David Rinken and my advisor, Professor Krifidis at UCLA. Here we consider a chemical process with input and output variables. To control the process output to its desired value, we can design a closed-loop system as shown in this plot. And since 1970s, advanced process controller that uses a process dynamic model explicitly in the controller design was proposed. And this mathematical process model can be developed either using first principle knowledge or using data-driven modeling approach with process input and output data. So compared to PID controller, model-based control improves closed-loop performance because the model accounts for inherent process characteristics such as nonlinear behavior and multivariable interactions. And over the past decade, machine learning has become very popular in process control community. Chemical engineers are dealing with more and more complex data than ever before, and machine learning shows great potential in process control. For example, machine learning techniques such as neural networks can be used to model the nonlinear systems for predictive control. Machine learning techniques like reinforcement learning can be used to develop database optimizer. And to develop a machine learning model, we first need to generate a dataset. And the dataset can be generated from industrial process data, lab experimental data, or extensive computer simulation. In our previous work, we have applied machine learning techniques to model nonlinear system using noise-free data. And we also incorporate the machine learning model within Model Predictive Controller MPC to predict state evolution. However, we know datasets from real industrial processes often involve noisy patterns, and the data noise can come from different sources such as sensor variability and common plant variances. So one way to handle data noise in training is to use data preprocessing. So for example, we can use Savicii-Golay filter to remove the data noise. But in this work, we want to design machine learning models to directly predict underlying the nominal process dynamics using the noisy data. So basically, we like to reduce the overfitting to noisy data, and we will use the dropout method to develop neural net models with weight uncertainty. So next, I will quickly go through the development of long short-term memory Lstm models and show an application to a benchmark chemical process example. So we will cover both Gaussian and non-Gaussian noise in Lstm training. And here's the class of nonlinear process system we consider. It's in the form of x dot equals f of x plus g of xu plus h of xw. X is state vector, U is manipulated input vector bounded by an input constraint, the capital U, and W is the bounded disturbance vector. And we also made some general assumptions for the control of nonlinear process systems. For example, Fg and H are sufficiently smooth. The measurement of process state X are available at each sampling time, where delta is the sampling period, and the steady state of the nominal system is at the origin. And lastly, we assume there is a controller phi of x that can stabilize the nonlinear system at the origin. And among many types of recurrent neural network, long short-term memory LSTM has demonstrated its advantages in modeling dynamic system with large time lag. So LSTM model is typically designed with the structure in this plot where we have several states. I is the output from the input gate, F is the LSTM forget gate, C is the cell state, O is the output gate, H is the internal state, and X hat is the predict output. And we apply the LSTM model to a chemical process example. So here we consider the CSTL with second order exothermic irreversible reaction from reactant A to product B. The system has two states, the concentration of A, Ca, and the temperature T, and has the system has two manipulated inputs, which are the inlet concentration ThA0 and the heat input rate Q. In our previous work, we developed recurrent neural net models to capture the nonlinear dynamics for all the states within this operating region omega rho using noise-free data. And it shows that the RNN model can capture the process dynamics very well. So the question is, what will happen if sensor measurements are corrupted by noise? So we first consider a Gaussian noise on both concentration and temperature measurements. We calculate the mean square error between the Lstm predict values and the actual noise-free values. So we train two models, one using noise-free data, the other one using noise data. So from the table, we see Lstm trained with noise-free data has better performance, but both networks have sufficiently small MSEs. In other words, the Lstm using the noisy data can also capture the process dynamics very well. So to provide an insight on the denoising capability of Lstm, we calculate the relative contributions of Lstm internal dynamics and the noisy input. The figure on the left shows that the time evolution of Lstm internal states, which is the black profile, is smoother than the Lstm input network, the red profile. And also we can see the norm of the internal state is greater than the norm of Lstm input. So this tells us the Lstm internal states play a dominant role in the prediction when using noisy data, and also explain why the Lstm network can predict true states even using a noisy dataset. And then we study the denoising capability of Lstm networks for different noise levels. And we calculate the root mean square errors of 3 Lstm networks trained against different noise levels with small, medium, and large variances delta. So in this figure, we can see the Lstm model trained against small noise perform better in small noise level, but becomes sensitive to large noise. However, the Lstm trained against large noise is less sensitive to noise level because it relies more on the internal state. So this explains why the neural network trained on a noise-free dataset could be extremely sensitive to small perturbation in real implementation. So to avoid that, people sometimes intentionally introduce noise into training to improve its robustness. So next, we consider industrial noise, which follows a non-Gaussian distribution, and we will use the dropout method to improve its performance. So here's the industrial noisy data from an Aspen database, and we first extract the normalized industrial data noise and apply it to our CSTI example. So we first try the standard Lstm training, and it turns out the standard Lstm cannot handle the non-Gaussian noise in this example. And then we use the dropout in the Lstm training. So dropout is widely used in neural network to prevent overfitting by randomly masking network units. So we take advantage of Monte Carlo MC dropout, which is proposed in Gao and Garimani's work. So the main difference between MC dropout and normal dropout is that the MC dropout will apply dropout at both training and testing phases. So the main idea is to define a binary variable z of Bernoulli distribution representing the weights being dropped out or remaining unchanged. So the predictive distribution of Lstm output is approximate using Monte Carlo simulations. In other words, in testing phase, we carry out a number of forward predictions and do the average to get the final prediction results. So here we calculate the MSE for the open loop Lstm prediction. So we have three models, the Lstm trained using noise-free data, using noisy data, and the dropout Lstm trained against noisy data. So the table shows the dropout Lstm has better MSE results than the Lstm with noisy data. And the figure here also shows the MC dropout result, which is the red profile, is closer to the ground truth, the black profile, compared to the standard LSTM prediction, which is the yellow profile. Okay, so lastly, we use the Lstm model to predict state evolution within model predictive controller MPC. And we consider 4 noise levels, and we use MPC objective function value to indicate the closed loop performance. But basically, a large objective function value implies slow convergence and high energy consumption. So from the table here shows the standard LSTM model has worse closed loop performance, and also the Japa LSTM model has significantly improved closed loop performance in the small and medium noise levels. So which implies the Japa LSTM model can work better when the noise level fall within this range. And here's one of the closed loop simulation results from the standard and Japa LSTMs. So we can see the Japa LSTM has better closed loop performance in that it settles at the steady state more smoothly and quickly. So with that, I'd like to conclude my talk. So we first investigate the case of Gaussian noise and show that the standard LSTM can mitigate the impact of Gaussian noise. And for non-Gaussian noise, we use MC-Japa methods to reduce the overfitting. So by applying the LSTM training method to a CSG example, we show that the Japa methods has better open loop and closed loop simulation results than the standard LSTM. And thank you for your attention. I'm happy to take any questions.